Greetings everyone. In this video I'm going to be demonstrating a basic return-oriented programming exploit using the ROPgadget tool. The source code I'm going to be using for this demo is actually exactly the same thing that I used in the previous demo, so if you've already downloaded it, you don't need to do so again. Now, the first thing I want to do is show you the difference between static and dynamic compilation because it's going to be relevant for this exploit. So I'm going to take my source code here, I'm going to compile it into two different binaries. The first one I'm going to call example 3.1D because it'll be dynamic, and this does not require any kind of special compilation flags. So there we go. The second one I'm going to compile it with the -static flag, same file, and I'm going to call this example 3.1s. Now, the first thing to notice, if you look at the size of these files, is the static file is significantly larger than the dynamically compiled file. And this makes sense, because in the static binary, all of the libraries that this executable is using are compiled into it, into a single file, whereas in the dynamic version, any libraries it uses are called in during runtime. So let's see what this actually means by looking at the binaries themselves. So if I open the dynamically compiled version in GDB here, and I run it, and this is going to crash, and I don't care. I just want to look at the memory maps, and you can view this with PETA's vmmap command. And as you can see here, I have the binary itself, and then I have libc and loader and a bunch of other miscellaneous segments that I don't particularly care about. So those two libraries are the ones that are being called in during runtime. Also, if I look at the overflow function, when I call string copy, which is in libc, I have the address here, and I get the name string copy at plt, which is the procedural linkage table, which is just a way of getting symbol names, meaning things like functions, at runtime. So that's the dynamic version. So let's take a look at the static version. Run this again, it's going to crash, I don't care. I look at the memory map here and notice that there's no libc, no loader, there's only the binary itself and some miscellaneous segments here like the stack and the heap. Also, if I look at the overflow function, when I have my string copy, it doesn't say string copy, it just has an address, because with a static version there are no symbol names to load from libraries, so all you have is the function address. Now, this is going to be relevant when we try to generate our ROP chain, as we'll see in a moment. Okay, so the first thing we have to do in order to use the ROPgadget tool is to install the ROPgadget tool. Now, this is a simple Python module, so we're going to install it with pip. So just pip install ROPgadget. And okay, good, already done. So now I can run this using ROPgadget like so, and it is case sensitive, so you have to do capital ROP. And then I'm going to use the ROP chain flag and then -- binary, and I'm going to run it on both of my compiled binaries. First the dynamic version, and I'm going to redirect this to a file I'm going to call ROPdin, and then I'm going to do the same thing with the static version and redirect it to a file called ROPstat. Okay, so let's take a look at these and see what happens. So looking at ROPdin, I have 99 unique gadgets, which is really a very small number, and it tried to automatically generate a ROP chain, which is an automatically executed way of popping a shell, and it was unsuccessful. It basically could not find any gadgets that it needed to generate the ROP chain. If I look at the static version, we will see, as I scroll down through here, that it found a lot more gadgets. In fact, it found 7,318 of them, and it actually managed to successfully generate the ROP chain. Now, in order to use this as an actual exploit, we're going to have to trim some fat here. So I'm going to start here right above Python. I'm going to do Control-Shift-Home to select everything above that, and then delete. And then I need to get rid of this leading space because white space matters in Python. So I'm going to do Control-H, do find replace, /T for tab, replace with nothing, and that gets rid of that. I then need to do two more things. In order to use this at the command line, which is how I'm going to do it, I need to add a print p statement here at the end, because p is what actually contains my concatenated ROP chain, which is strung together using this pack functionality. And then the second thing I need to do, just like in the previous exploit, I need to fill my buffer and my padding until I get to the return address. So I need to add padding here, and you can see it says padding goes here. So I'm going to do p plus equals a, just to fill the buffer, times 16. Why 16? If you watch the previous video, you'll see that I determined that 16 is the number of bytes between the start of my overflow buffer and my return address. So I'm going to save this here, and it detects it as Python, so it automatically colorizes it. The second thing I need to do is to make it executable. So I'll change the permissions there, and then I can run it. So I'm going to run this using example3.1s, and I'm going to pipe in the output of ROPstat. And I get a segfault, and that's cool. This actually harkens back to something I talked about in the previous demo, where at somewhere in here there is an invalid byte that is causing Python to interpret this incorrectly. And the way to solve this, again, just like I talked about in the previous video, is to enclose your entire command substitution in double quotes. So now when I do this, I get a shell, as I expect, because it is treating the invalid bytes as literals until they're passed into the program, thus allowing it to execute as I intend. And that's it. That's all there is to it. That is how to use ROPgadget to carry out a return-oriented programming exploit. Thanks for watching.